So I know this week is only chapter 11, and so I wanted to do something a little slightly different. I'm going to be doing chapter 9 from an additional data communications text, because I want to be able to focus on spread spectrum, because this is one of those important areas. Part of spread spectrum actually is things like dealing with jamming and interception, frequency hopping, and sequencing. When we start talking about our communication, one of the biggest things that we talk about is availability. But we don't always talk about confidentiality. And part of that is actually making sure that the signal can get where it's going, anti-jamming. Nothing can actually intercept and prevent that signal from going where it needs to be going. Again, all jamming. And some of the techniques that are used. A big part of that's going to be frequency hopping. I always start off week 4 with a frequency hopping question, just because it doesn't just have military applications, it actually does affect most of us in our everyday life. Our wireless, when the channels get overly saturated, how does the system know to jump frequencies to other channels? Big part of that is the actual frequency hopping. So, yeah. We're going to be talking about how the multiplexer actually gets fed from an encoder and a pseudo-noise generator. That way the modulator can put it on the appropriate channel or channels. One of the benefits here is it will actually be broadcasting over a larger group of channels. That way the frequency can be hopping between them. It also allows for the spectrum to have greater bandwidth. The receivers are using the same sequence for demodulation. The demodulators is fed into an encoder. Essentially, this is what we're looking at. We do a channel encoder. That also is fed into a pseudo-noise generator that helps produce the spread code, and then those get transferred over a channel. From those channels, the receiving end will actually demodulate it, and again will separate it back with spread code and our channel decoders. That way we can do an input and an output and have it modulated in such a way where it can actually traverse multiple channels, not having to rely on just a single channel. Because that's actually a really big thing, because when we have too much noise on several channels, or just a few channels that aren't evenly spread out, those channels get overly saturated. So let's talk about some gains for a second. So with the addition of gains, we're talking about the immunity from various noise and multipathing distortion. This means jamming. We're allowed to encode or hide or encrypt additional messages within our spectrum. Only the receiver knows the spectrum code. The important part there is, so when it gets sent over, the spectrum coding, or the spread coding, actually shows what portions of the spectrums are part of that encrypted signal. If you don't know what you're looking for, it makes it a lot harder to try to find it. Users that actually share the higher bandwidth, that things are our telephones, our CDM, our CDMA, our code division. You'll notice that chapter 11 was very heavy code division multiplexing. That's why I figured this tie-in chapter, along with frequency hopping, would be a perfect fit. So the next thing is, what are the pseudo-random numbers? So how do we get that random channel? So it actually is generated by an algorithm using an initial seed, our receiver. It actually is not truly random. It actually does it uses a deterministic algorithm, so it's not really random. That way we can actually use this type of algorithm to predict sequencing. So how does this tie back into frequency hop? Part of this frequency hopping sped spectrum, or FHSS, actually deals specifically with a seemingly random series of frequencies that are going to be broadcast over. It's not really random. It actually is done through a specific algorithm that allows best communication for those saturated frequencies. The receiver hops between frequencies and syncing with the transmitter. Again, it's not random. It is all actually very controlled. That way, if there's something like eavesdroppers, it's harder to see the frequencies that they're being changed to and from. Jamming on one frequency affects only a few bits. That means instead of having to jam just a few frequencies, for frequency hopping you'd have to jam several other frequencies, or you'd have to saturate other frequencies, thus no longer just affecting your one signal but additional signals. So that wouldn't really be very beneficial unless you want to jam multiple signals within an area, but that means you're going to be more noticeable. So it just kind of depends on the situation. So how exactly does this basically operate? So how we do this is, typically there's 2K carriers, frequencies forming 2K channels. The channel spacing corresponds to the bandwidth of the input, and they're using fixed intervals. 802.11 actually denotes the 300 millisecond interval. Some of the numbers of bits transmitted using some encoding schemes, it can be fractional. So what exactly does this mean? Because when we discuss this, it's hard to see what exactly this means. So here's a graphical representation of it. So we are using our 8 different frequencies, and here they are in relative to time. You'll see there is a pattern to it. It's just first it might not be very seemingly, but there is a channel 5, 8, 3, 6, 1, 7, 4, 2. You'll notice that they're hopping between 1 and 8 channels. I would imagine that they'll also repeat afterwards. If they were using additional channels, we'd be actually hopping between those channels. So how does the actual transmitter work? Here we have our modulator, and it actually goes into a frequency hopping spreader, and a big part of that is our pseudo noise, our channel tables, our frequency synthesizer, and that actually allows us to do our filter out. Half a love the nitty-gritty of this. I've never actually had to use any of this. It's just, it's nice to know that it's there, and there is something behind it. It's not just this magic. It's actually very precise. If you're an electrical or a wireless engineer, you'd have to know this. But I figured it'd be at least a nice little peek behind the closet, just so that we can see what's really there. For the receiving end, same thing. We have our frequency hopper despreader, which is the opposite of our spreader, and then again our pseudo bit noise, our channel table, our frequency synthesizer, so that we can actually decode and get decode and demodulate, so that we have our output. So the next thing is, so for frequency hopping, can there be different speeds? There can actually be different speeds depending on our frequency hopping needs. I have to love the math here. Generally, the faster the frequency hopping, the better the performance in noise or jamming. Meaning, it's a lot harder to supplement noise or to interject noise or jamming for faster frequency hopping spectrums. The slower, the easier. That way you can actually target specific frequencies at a more steady pace. So graphical representation for our slow hopping is, this will be a function of time, and this will be a function of our frequencies, and you'll see that it's very slow per cycle. Now if we actually change that to our fast, we'll see that it's actually a lot faster within our time, and it's the same frequencies. It's just because of our time, we actually are able to actually switch that several times a second, making it harder to jam. That way you have to know the specific frequency that you're on in order to do that. Again, performance considerations is the larger number of frequencies used, the better the resistance to jamming. And to noise, because again, you're continuously jumping different frequencies, so the likelihood that the frequency that you're jumping onto will be saturated is really low. Even if it is saturated, the amount of time that you're going to be at that specific frequency is very low or short, because we're dealing with time. So the likelihood of you staying on a saturated frequency for an extended period of time is very low. The amount of time that you're there is, again, very low. So now we have this thing called direct sequence spread spectrum, and that actually helps in propagation. It helps with using wider frequencies. It actually also increases our frequency, or our bandwidth per frequency. Basically, it's very similar to our frequency hopping, but it doesn't do the same way. What I mean by that is it actually does not alter any of the spreading code bits, but what it does is it actually allows combination of our signals. And it's all in the methodology and how it does it. I've actually never used direct sequence spreading. Most of my training has all been in frequency hopping, but I just wanted to point out that frequency hopping is only one example of many. So now let's take a different look at our CDMA. And again, remember that our CDMA, it's just a multiplexing technique, and it's being used over a spread spectrum. And so what that means is we have several coding for multiple users, but that way we can share the same channel with an appropriate break. So here we have user A, B, and C represented into different message codes, and they're encoded in such a way where they're going to be different signals. So let's make the consideration that A is going to communicate with our base. So we know our code for A, and we actually want to send a very specific pattern. The decoder will ignore all sources when using A's code to decode it. Basically what we're doing here is we are looking at the combined messages, and we're seeing what we're going to have to decode and encode, because as we get 3 user signals coming through, we're going to start ignoring portions of the signal that do not match our filtering. So let's say that we have A, B, and C, and A, B, and C are actually communicating, and we only want to filter out filter A. We only want to see A. So it would be filtering out B and C. So the chip could actually do that one of two ways. It can filter out B and C, or it can filter A and just decode the A portion. Kind of just depends on the technique that is currently being used. Also depends on the chip that is being used as well. The CDMA is actually an N+ process, which means we can actually encode several users to one channel. It just every user is going to use its own P and frequency, or its own sequence, so that way our sender and our receivers will know how to decode whatever is being transmitted. Here's a graphical representation of our multi-in series frequency. Here would be our first user, our second user, our N+ user. Any additional noise that would be filtered on our line. But how does that actually encode onto our using CDMA? And here we go. This is our encoding. Here we actually have our 7 users separated and sequenced in such a way we will actually use our channel 0 code. We will actually combine the signals, send them out. That way our receiver end can actually finish decoding them. And that's actually this chapter in a nutshell. It's always interesting to start looking at how our sending and receiving chips actually truly function. Normally, if you don't have a good understanding of digital logic, some of this is not the easiest to learn. But at the same time, we're not electrical engineers, so we don't have to understand it to this nitty-gritty. But I just thought it would be interesting to share because a lot of people always ask questions about how this really functions, and they always think that it's all very scary, but it really isn't. This is just, again, a very simple overview of how most of this works. And thank you. I hope you guys have a great day.